recording. We're in business, as they say. Okay, so now let's go to chapter 8. And the DC book. And get our worksheet up. And we're almost there. So, chapter 8 is on capacitors, and there's some good problems in this chapter. So basically, we're just going to try to get through them. And there's a couple that I have assigned to you. We're going to do more than what I assigned, but we'll get those done as well. Okay, so chapter 8. So if I had these two capacitors, what would be the total capacitance for that circuit right there, number 1? Well, you would use the parallel rule, right? Excuse me, the series rule, because they're in parallel. So you use the opposite. So instead of 3 and a 2, it is a, what, 5, right? So it's 5 microfarads for number 1. Number 2, you have 3, and they're in parallel, so you would add them together. There is a 1 microfarad, that's 1 times 10 to the minus 6th. There are 500 nanofarads, and then there is 2 microfarads. So this is 1 times 10 to the 6th. This is 500 times 10, nano 9 minus 9, and this is 2 times 10 to the minus 6. So it's 1.5 and 2, giving me 3.5 microfarads. Okay, so that is additive. Here you have 2 in series, so you do what? Use the parallel rule. So it's 3 in parallel, 3 times 6 over 3 plus 6 microfarads. Or 18 divided by 9, 2 microfarads. And here we have 3, so you have to use the 1 over 1 over rule. So it's 1 over 10 plus 1 over 30 plus 1 over 50. And that is what? I don't know. Do our calculators and find it out. Does anybody have any problem with the 1 over 1 over rule? Okay, let's try it. 1 over 1 divided by, parenthesis, 1 divided by 10 plus 1 divided by 30 plus 1 divided by 50 in parenthesis equals 150 or 6.532 or 6.521 farads. Everybody get that? The 1 over 1 over rule, that makes sense to everybody? Good. Number 5. Determine the voltage across each capacitor in the circuit. So this is one of those that I told you really don't have to memorize, but how do you do this one? Number 5. Okay, this is one that's not easy. So you basically have to find C equivalent. So number 5, you have to find C equivalent. And the same way with number 6. 5 and 6 are the same thing. C equivalent is equal to what in that case? They're in series, so what is your C equivalent? 1 over 1 over roll. 1 over 1 over 10 plus 1 over 20, or what? It's about 6.7, I think, but let's try and get it. 1 divided by, parenthesis, 1 divided by 10 plus 1 divided by 20 in parenthesis equals 20 over 3, or 6.67. 6.67 microfarads. Now we use the equation C equivalent is equal to Q over V. Now V here is what? 12. And C equivalent is 6.67. So what is Q? Looks like Q to me would be C equivalent times V, or 6.67 times 10 to the minus 6th times 12, or what? Or 80.04 micro, and they have units of coulombs. We really don't care too much about coulombs or units of it, but that's what the units are, coulombs. Okay, so that's our equivalent. Now, that's what gets charged on each of these plates. So as you go around here, you get that charge plus to minus on each of these. So you get it plus to minus here and plus to minus here. So you get that charge. You follow me? It's the same. It's not the same electrons. You've got some electrons trapped in this part of it, and then you got some trapped over here, and you got some trapped down here. So you've got basically electrons trapped all over the place. But because they can't move, the electrons can't move this way, they can't move that way, they just are trapped right in that little spot right there. But the charge on that plate is that. And the charge on that plate is that. It's the same. So now basically you go back and you ask yourself, what is the voltage on each of these capacitors? So you now say, okay, so that charge Q of 80.04 times 10 to the minus 6th is equal to C, which now is 10 microfarads times the voltage across it. It makes sense? Now the voltage across these two have to add up to what? Better add up to 12. Why? Because the voltage run in a closed loop has to add up to 12. Does everybody follow that? So here's the trick. You got to find C equivalent. And that's that problem. So what would be voltage across that? Voltage across that one looks like 80 approximately divided by 10 microfarads on microcoulombs on the, or microcoulombs on the top, microfarads on the bottom. This is 10 to the minus 6th. This is 10 to the minus 6th. The 10 to the minus 6th both cancel out, so it's 80 over 10 or 8. So the voltage up here is 8. What does that leave this one? Better be 4. And you can go back and look at it, and you can say, okay, so 6.67 is equal to times, or excuse me, you can say 20 microfarads, which is my C, times okay, no, voltage is equal to, here, I'm going to do it this way. Voltage is equal to, if you move voltage over here and C equivalent down here is equal to charge 6.67 times 10 to the minus 6th. So voltage of this one is, CQ down here is 20. So it is equal to what? They're equal to be 4. This is not right. This is, excuse me, this is 80. 80 divided by 20 is 4. And that's what that is. All right, so I don't want to confuse you, but that's how you do that problem. You have to find C equivalent first. And once you find C equivalent, you plug it back in and you say, okay, now I have my Q is equal to my capacitor times the voltage in general. And here it is 880 is equal to 10 times the voltage, which is 8, or 20 times the voltage, which is 4. And that's it. Sorry to confuse you, but that's how that's done. Okay, so now let's go on to 6. Same thing. Now you have 3. Okay, now you've got 3 of these guys. So what do you have to do first? You got to find C equivalent, right? What is C equivalent here? Everybody do this. Okay, you tell me what C equivalent is. It's 1 divided by, parenthesis, 1 divided by 10 plus 1 divided by 20 plus 1 divided by 40 in parenthesis. What does that equal? See if you can get it. Okay. Raise your hand if you get it. Get it. Raise your hand if you got it. Okay. I want to see hands. You got it? Okay. I want to see hands. Okay, you can drop them. Just I don't want to. Anybody else? I want to see when you get it. I want to see your hand. Okay, good. Anybody else? All right, we're moving on. But let's. I want you to be active in this and try to get these as well as when we were going through this. Okay. So now you found C equivalent. So C equivalent is equal to that. Okay. So now we've got this equation. C equivalent is equal to Q over V. I want to find this value right here. And my V is equal to 24. So Q is equal to 5.71 times 24. And what is that? What is my total charge? 137.04 microcoulombs. Any questions so far? Now I go back and I plug in C equals Q over V, and I've now got this guy. This is 137.04, and it's the same across all of them. And I plug in, if I got a specific C, I can find my V. So V is equal to Q over C. Everybody follow that? So now you can say 137.04 divided by 10 is what? That's across this one. What would that be? It's about 13.7 volts, right? What about this one right here? It's about half of that. Maybe about 6.8. V across the 10 microfarad is about 13. Voltage across the 20 microfarad, it would be about 6.9, 6.85, 6.86. V across the 40 would be about 3.42 or something like that. And these all have to add up to what? 13, 6 point something, and 3 point something have to add up to what? 24. Any question? Okay, that's that one. All right, so if you, again, you do not have to memorize this. I'm telling you, you can just write this on the corner of your paper, that your study sheet that you build up, and you can have this step by step by step. And there's about 2 or 3 steps here, and they're not hard, but that's that one. Will they ever ask this on a test? I don't know. That's one of those questions that you might have to think about, because I do stress it here. So you might want to put it down as something you want to know. Okay, so now let's go ahead and look at number 7. Okay, so now it says determine the initial value across each of these components. Now, this is this Owens Community College. And by the way, if you're from Owens Community College or other community colleges, but basically Owens especially, you guys do a good job. So if you're from there, good for you. And it is you do learn this stuff pretty well. You do it very well. Ready, set, go. At go, you turn this on. In other words, before t equals 0, or whatever you say your go term is, this is off. But at that instant where you turn this 10-volt supply on, everything starts to happen. So that's what we call transient analysis. We talked about in a lot of detail about, steady state analysis and transient analysis. This is transient analysis. We're in a DC room. We're talking about a DC supply, but we're talking about a capacitor. And this is one of those times when it doesn't immediately snap to and go to its final value. It takes a little while to get there. Talked about the hose emptying out, the flywheel on a machine, or your tires spinning. They don't start out immediately. They take a little while to get going. That's inertia. It's stored energy and that type of thing. So they basically don't get going immediately. So what would be the initial value across each of the components of this circuit? So here you have to lead with the capacitor, and you draw this as a circuit at initial, and you draw just for initial conditions. All right, so what do you do in this situation? Well, here's your 10 volts. Here's my 2K. Here's my 3K. Here's my capacitor, but what do I do about the capacitor? I go right through it, because it's a short, 0 volts. Everybody agree with that? It's a short. So I do this, or I can just draw straight through it. And then I draw 4K. And what do I have left? I have a chapter 4, chapter 5 problem, don't I? Don't I? And that's all this is. So what's the voltage across each of these components at that instant in time? What is the voltage across each of these components? Well, you got to figure it out. You just have to go down and figure it out. How would you do that? Well, you would say combine the 3 and the 4K into one resistor. What would that resistor be? Well, it's 12 over 7. What would that be? 12 sevenths. 1.71. Okay. All right. So then I use voltage divider. 10 volts. 2K. 1.71K. What's the voltage across the 2K? Voltage across the 2K is equal to what? 2 over 2 plus 1.71 times 10, or whatever that is. Everybody follow that? Voltage divider is your best friend. All right? Everybody agree with that? Now that's the voltage across the 2K. So basically you've reduced this down to something else. But you're only asking about it one instant in time. All right? So what would be the voltage across the 2K? 2 divided by 3.71. 2 times 10 divided by 3.71 equals 5.39. What about what's left? Well, I bet what's left is across here, which would be about 4.4 or 4.61, right? 4.61 is what's over here. So 4.61 is what's over here. 4.61 is what's over here. And this is 5.39. And you say, these aren't nice numbers. They don't have to be. They just have to come out to whatever they are. You don't always get nice numbers. You don't always get 2, 3, 5. You don't always get nice numbers, but that's what the answer to that one is. What would be the steady state voltage across each of those components? After a while. What would it be after a while? Okay, let's go back and do that. After a while, this circuit becomes this. 10, 2K, 3K. And what is this up here? An open circuit. Is there any current that goes down that way? No. If there's no current that goes down that way, what is the voltage across the 4K? 0. So now we just have this little loop right here. Okay, it wiped this whole thing out. You say, well, who would ever design a circuit like that? I don't know. But the answer to the question is, this is, yes, sir. They're the same. They're the same. Okay, yeah, good question. Always good question. Don't ever fear to ask a question. The only dumb one is the one you don't ask, okay? All right, so what is the voltage now? You can look very easily and say what the voltage is across the 2K. What's the voltage across the 2K? Just by looking at it. What is it? There'd be 4 volts, right? Why is that? It's 2 over 5, 2 or 2 plus 3 times 10, or it's 4. What's the voltage across the 3K? It better be 6 volts. Okay. It's very, very doable. Okay, what's the voltage across the 4K? So what's the voltage across the capacitor? Ah, the missing link. What is the voltage across the capacitor? Voltage around any closed loop has to add to 0. What's the voltage across the capacitor? This is 0, this is 6. What's left? 6. It's not 0. It's charged. It's just sitting there fully charged. There's no current flowing, but that puppy's fully charged. Okay? It's charged up. See? Now, why would we ever do anything like that? Well, you can charge it, you can discharge it, you can use that time constant to give you a time delay. Okay? Why do they put capacitors around at the entry to boards on computers? Gee, I didn't know they did that. Well, yes, they do. Why do they do that? To trip out all the excess DC voltage. So in other words, it's kind of like if you have a stray DC voltage from this board to this board, and then you put a capacitor in the middle, it blocks it. You say, what? It blocks it. So DC will be blocked. And it's just another thing that they do with capacitors. Capacitors are used a lot, and I'm not really the expert on them. And I'm not. By the way, if you want to have somebody fix your TV, don't ask me. I can get it sometimes, but I'm not an expert at it, and I'm not an expert at that type of thing. Although, I'd like to think that I could eventually figure it out, but I'm not. We had a guy that we worked with that was one of the guys that I taught with when I first here, and basically at that time, we had people that fixed TVs for a living in our program, and they were taking the program so they could learn to fix TVs. and really be good at it. And there were some who did and were and made money at it. But that's gone. I mean, it's literally everything is on a board, and when it fails, it just gets thrown away. That's gone. That whole industry is just, anyway, it's okay. It doesn't matter. Don't worry about it. And don't worry about AI either. I told you the other day, don't worry about, I think I told you, did I tell you about don't worry about AI? Did I say don't worry about AI in this program? Did I tell you that? Don't worry about AI. Again, you should be friends with AI and you should learn about it, but it's not going to take your job. Okay? To the best of my ability, I'm going to stick with that. Now, some people will say, oh, that'll take everybody's job. No, it won't. Not these kinds of jobs that we have. And part of it is because most of the things that you do are one of a kind. And AI depends on thousands of inputs in order to be able to, thousands of responses in order to be able to come up with an answer. Okay, so you're building a onesie of something. They'll never get those down and be able to master how to answer those. They will never be able to do that. Okay, so what you're building most time is a machine that is a one-of-a-kind machine. Okay, now we're down to number 11. Here we go, number 11, time constant time. All right, so this is a time constant. This is a DC room resistor and capacitor. And again, when we studied this stuff, I told you that basically there is a day coming when you will study this as with a differential equation problem, but you're studying it today as an algebraic problem. And we just have to accept the fact that you get this mysterious answer that comes out at you, but basically you say, okay, I am a detective, and when I see this, I do this. Okay? When I see something over here, I respond a certain way. When I see something over here, I respond a certain way. When I see a resistor and a capacitor and a DC, I respond by writing in a certain type of equation, and that's exactly what we're hitting here. DC supply, resistor, capacitor, and the resistor looks like Thevenin. All right? So this looks like a Thevenin circuit, doesn't it? There's one resistor and there's one resistor and one voltage supply. And the only thing that's new is that little switch in there. So that little switch in there says ready, set, go. That's all it is. Go. And when it happens, you write your equation. So basically your equation is based on t equals 0. In other words, the time when you start this thing going. So at t equals 0, you start writing an equation based on time. It's a time-related equation, all right? So what do you write? Well, it's a canned expression as far as we're concerned. We don't care how we got there. We just care that it's there. So we write what? What's the voltage across? And it's always the voltage across the capacitor. Voltage across the capacitor is 5, that input voltage, times, if it's a charging circuit, which this has got to, which when it closes, follow me? When that thing closes, it's charging. When it opens, it's discharging. But here, when it opens, it doesn't do anything because it just sits there. 5 times 1 minus e to the minus t over tau, and that's it. Where tau is equal to RC. R times the resistance times the capacitance. And then you basically plug that in, and you can find, at some instant in time, what does it look like? It looks like this. That graph versus time, voltage across the capacitor, like that. That's it. Now, what do you use these for? All kinds of stuff. That's what it is. That's your equation. That's the answer. So what do you do? Well, here you just plug in the 5 right there, and the 1 minus e to the minus t is just a standard. What's tau? R times C, 100 times 200 times 10 to the minus 9th. And you're done. All right? Any questions about how that's done? In other words, I'm a detective, I see this, and I do this immediately. I just go immediately to this answer. Now, if you were in differential equations, which you will get to later, and you'll get to solve this with a differential equation, you will have a loop equation, and you will solve it for I. Okay? And you'll write, what's the voltage around the closed loop? I'll do it, okay? So the voltage around the closed loop is that voltage that resistance, and that capacitance, okay? And here it is. Voltage across the capacitor is equal to what? E-L-I-I-C-E. So I is equal to C dV over dt, all right? So again, V is equal to I over C integral dt, okay? Integral I dt. So it's basically the integral, and that's your equation. So the voltage across the capacitor, here is minus 5, so you'd say minus 5 plus I times R plus integral 1 over C integral I dt equals 0. And that's your equation. All right? So that's what you're coming down to later. But you're not going to do that today. We're just going to look at it and say, boom, there's your answer. So the answer to this is this. Does that make sense? We're kind of jumping over that because you haven't had differential equations yet. But when you get to differential equations, you'll actually do this and get this. Any question? As a matter of fact, the solution to any first order differential equation is that right there. So now you know the secret sauce of first order differential equations. Right there it is. Even though you didn't get it by studying differential equations. See, I had to study differential equations before I got to my circuits course, except for the fact that I was a semester behind in my math. So I got to do it both at the same time. I got to study differential equations and this stupid equation at the bottom all at the same time. And oh my goodness. I got a B in the circuits course, but when I got to differential equations, I could teach the course because I had all the differential equations already done. I knew exactly what he was going to say the next sentence out of his mouth because I already had them. But anyway, that's neither here nor there. But that's what it is. So if you're interested in that part of it, that's what it is. Okay? If you're not, forget about it. Just take this and run with it. But you're looking as a detective for this particular set of circumstances, and you're going to write this. That's interesting. That's very interesting. But it's based on this. First order differential equation. Either a capacitor or an inductor, but not both. All right? So with a capacitor, there it is. Voltage. 1 minus E minus T over tau. Tau is equal to RC. Next chapter is going to be L over R. So again, you're going to have these little variances, but basically it's the same thing. Okay, and instead of V, it's I. It's the same thing. What about this one? Everybody, take 20 seconds and write the equation for this guy. Write for the voltage. Oh, it says find the capacitor voltage and circulating current 20 milliseconds after the switch is closed, and then 10 seconds after the switch is closed. So this is even further. This is writing the equation and then evaluating the equation. So at 200 milliseconds, let's just do that one, 200 milliseconds, and just find the voltage. And then we'll go back and we'll find the current. Okay, so you do it. Don't look up here. Anybody looking? Don't look. Look down. Do your own, and I'll do mine. Okay, and we'll see if you got the same answer. All right. If I see anybody looking up, it's not good. No, I don't care. All right, you can look up. What'd you get? You get these values or not? What's your voltage? Voltage across the capacitor is 13.21, right? Is that right? See how I got it? I evaluated the equation 24 times 1 minus e to the minus t over tau. Tau is equal to RC. R is 25K. C is 10 times 10 to the minus sixth, or 250 times 10 to the minus third. I wrote that in the equation, 24, 1 minus e to the minus t over 250 times 10 to the minus third. But you evaluated at 200, so that's minus 0.8. So you write in your equation 24 parenthesis 1 minus e to the minus 0.8 equal 13.21. Okay, so that's the voltage across the capacitor. Now, what's the current through the capacitor? Well, in order to get the current through the capacitor, you got to go back to the resistor and say, voltage around the closed loop has to always add to zero. So if it's 13.21 here, what is it up here? What's left? 10.79. So the voltage across that resistor is 10.79. Divide that by 25K, and I come up with 0.431. Okay? What will it be at 10 seconds? What's the voltage across the capacitor? It's going to be the full 24 volts. What's the current through the circuit? It's going to be zero. I can tell you that. It's so close to zero, you don't even care. All right. Any questions about that one? Now let's go down to 15. Yes, sir.
What is the
Huh?
what is their unit on tab? Like, is that seconds or is it just like number? Like
Which one?
the tab receipt?
It's a unitless number. Oh, it's units of time, units of seconds. Yeah, units of seconds. You say, so I multiply a resistance time a capacitance, I come up with seconds. The answer is yes. Units, yeah, they do. Very good. All right, so now you turn it over and turn it upside down, and what do you get? So I got this wrong. I got this upside down, didn't I? I wrote it upside down. Daggone it. The answer is minus. Uh, okay. The answer is the same, except for the current here is the minus of that. I'm sorry about that. I did it upside down. Nobody caught me on that. I did it upside down. It is minus that, because the current flows this way instead of that way. And the voltage is plus on the bottom, so that it's minus 13. The voltage is minus 13.21, and the current is minus 0.431. That's it. That's the only difference, but I'm sorry. Did it upside down. Any questions? What about this one? Ah, this is both. What do you do when you flip it to position 1? What do you have? You have a charging circuit, don't you? What is the R? 1K. What is the C? 1 microfarad. What is the voltage? 10 volts. You're in. When you flip it to position 2, what happens? There is no voltage to charge it up, so now it discharges through the resistance that is in series 1 plus 2K or 3K. So your resistance on the discharge side is 3K. Which is going to happen faster? With this, because your R is smaller. When your R is bigger, it takes it longer. Okay? And in reality, what is this switch? It's not a physical switch. You're going to switch like this. What is it? It's a transistor. Okay? So when you're doing this kind of thing, you always look at this guy and say, what is really going on here? Is this something I'm ever going to use? No, not exactly the way it is right now, but you're going to see a transistor switching it back and forth. Okay? All right, moving on. Moving along. Moving on. Okay, now this one is the same thing, but I wanted to get down to one. I asked you to do number 24 and number 25. So this is the one I actually want you to do out of the homework. The only homework I'm asking you to do out of chapter 8 is this one right here. And this is because this one requires what? Thevenin. And I had one student come up after and said, I don't know anything about that. But on the other hand, you do need to know how to Thevenize. So if you haven't learned how to Thevenize yet, or if that's something that's foreign to you, we're going to go through it. And I'm going to refer you back to the chapter that talks about Thevenin in this book and tell you that you need to review it. And if you do need to review it further, we can have more time with it. But if you're not comfortable with Thevenin, you need to take a little bit of time to learn how it works, okay? Now, it's a strange duck. Because why? Because you have to put on special glasses to make those rules apply. And if you do them exactly the way that they're supposed to be put in there, you will be okay. But if you don't, it won't work. So 24 is Thevenize this circuit with up to this point, because this is not what you want. You want this. Add the capacitor. That's what you want. What you got is something else. That makes sense? So when you flip the switch to position 1, you don't have this, you have this. But what you actually have here is this, 90 volts, then this, 12K, and then this is 6K, and then you've got this, okay? Makes sense? All right, so what do you got to do? You must Thevenize it to get to this mechanism. So how do you do that? V-Thevenin, you take scissors and you cut it right there, right? You cut it and you look at the circuit like this. 90. As if it was cut like that. Forget about the capacitor. The capacitor is not part of what we're talking about right now. You actually take a pair of scissors and you cut the circuit and you let that part of it go. It's gone. Now you work on this circuit and you find, what is the voltage across here? 12 and 6 is what? That better be 30 volts. Okay? Everybody agree with that? So that's equal to what? That's your V-Thevenin. It's the voltage across the output with the thing snipped off, with the other part snipped off. V-Thevenin is easy. R-Thevenin is the one everybody gets a hard time with. Okay. How do you do R-Thevenin? Well, you short voltage supplies, you open current supplies. So is this a voltage supply or current supply? So it's a voltage supply. You short your V's, you open your I's. Open your I's, okay? So you open the I's, you short the V's, and that's how you start. Then you ask the question, what would be the resistance from here to here? You walk backwards. You do not go left or right, you go right to left. Right? And that's the hard part most people have. I'm in Toledo, I want to get to Bono, or I want to get to Bowling Green. So how do I go? I can either I can go right down I-75, or I can go over to Fort Wayne and come down and go back over, either way. But when you do that, is this in series or parallel? It's in parallel. Okay, if there's a dangling resistor out here, you have to use it. You have to walk through that separately. But this one does not have a dangling resistor. So what is R-Thevenin? Does everybody remember this? Does this bring back? Some of you are kind of giving me the yeah, but some of you are kind of like, I don't know. I don't know. You better know. This is one that you should know. All right? How do you find R-Thevenin? Because we use it in AC circuits as well as DC circuits. It's not like We just had it for that, and then that's it. That's the end of the story. Nope, we use it again. So again, what is R Thevenin? What's 12 parallel with 6? It's 4, but I'm not sure. Let's go look. 12 times 6 divided by 18, right? Yep, it's 4. This is an easy one. R Thevenin is equal to 4. Now you go to war. Now you put the thing back together again, and I'm out of space. Remember that V Thevenin is 30 and R Thevenin is 4. Now we go back, erase the blackboard, and start over again. So now we start over again with a voltage supply of 30 and an R up here of 4K. And then we do our equation. And you get the right answer. You say, does this work all the time? It does. How do you prove it? I don't want to prove it. It works. Is this just something that you invented out of thin air? No, this is a mathematically provable formula. It's called a theorem. Okay, it's provable. So what is your answer for the charging cycle? V sub C is equal to what? 30, parenthesis 1 minus e to the minus t over tau, which is tau is equal to what? 4k times 100 times 10 to the minus 9th. That's it. Now you can go to war and find out at any instant in time what it is. You can draw the circuit, you can draw it, you can do it. It's all done. Now, when you discharge, oh, and by the way, when it fully is charged, what's the voltage going to be sitting on this capacitor? 30 volts. So when you discharge, that's your charging circuit. And a charging circuit answer. And you say, what's the voltage across this? What's the voltage across this? It's a painful process to find, but you can find it. But what's the voltage? How do you write the equation for the capacitor on the discharge side? The charge and the discharge. V sub C is equal to what? 30 e to the minus t over tau, where now tau is equal to what? 1k. It's this loop right here. And that's how you do that question, number 24 and 25. And that's all you owe me as far as homework for this chapter. Okay. How late are we supposed to go? Are we supposed to go to 9:20? We got 10 more minutes. We can go 10 more minutes. Any questions about those two problems? You owe me those two homework problems, and they're due. They'll be due on in a week, but problems due. I say today, but no, you don't have to do them today. If you want to do them, if you can get them to me next Wednesday, that would be fantastic. Next Tuesday, that would be fantastic, or Thursday, and I'll take them. Any questions about that? I say 125, which is, I didn't do that right. I didn't do that 125 right. I just said, whenever. But I want you to have them done next week, hopefully next Tuesday or next Thursday, if possible, by then. All right. Chapter 9 is the same thing, only different. It's the exact same type of thing, only instead of capacitors, we use inductors. And where capacitors charge voltage, inductors charge current. Okay? Or they store. Capacitors store voltage, inductors store current. All right? And why is that important? Well, when a contact opens on a motor starter, what is a motor. It's an inductor. So when it opens, and when a motor opens, there's a contactor there, and that contact, that's not a capacitor, that's a contactor. It opens, but current can't stop immediately. So what it does is it drips across, and there's little bits of electrons that every time you open and close that, every time you open that contact, there's electrons that jump across, okay? And they take with them copper. So as you look at motors that start and stop a lot, what do you see? It's called pitting. And that's why you have to after so long a time, you have to go into a motor. It's got a motor starter on it. That's got a manual starter on, or that's got a starter that opens and closes, and change out those contacts, because you cannot start and stop inductive current immediately. It won't do like this. Current in an inductor will do like this. And when you stop, it won't immediately do this. It will do like this. So this little piece right here is where the damage is done, if you want to say damage. It's not really damage, it's just that. Okay? So that's a side to this. Now, again, it's not a big deal, but it's how it is explained, and that's exactly why many times you have flyback diodes in circuits to be able to do that. You've heard of snubber circuits. Many times those are RC time constant circuits. So a snubber circuit many times is a RC circuit that will allow a solenoid or something like that to not have such a big inrush of current. In other words, it takes a little while for it to build up. And again, there's different types of them, but if you turn on a circuit that's got a big fat solenoid on it, the current draw immediately is pretty high, so you put an RC snubber on it in order to make it not be quite so harsh and not burn up your output cards. So again, these are all things that have to do with the storage of energy and keeping it from being a, how do you want to say, harsh, so you don't burn things up. So you put snubbers in and that type of thing. So again, RC time constant snubbers, or there's other ones, MOVs, different types of snubbers, but one of them is an RC time constant, RC circuit. So what do inductors look like? Okay, they really aren't very interesting things. I mean, you say, well, and you can understand a little bit about circuit analysis and magnetic circuits because you have current and you have a magnetic field, and that's what that shows. That's a magnetic field around that wire. And that's why you lay wires in a trough or something like that. You only put high voltage wires, or you don't put analog wires in with a bunch of motor wires, because they will crosstalk, and this will crosstalk to those other wires and give false signals. So again, these are things that you don't think are important, but in some cases they're very important. Okay, so here is an inductor. That's what an inductor looks like. It does create that current lag, if you will, and it does that build up and then let go, that type of thing in a DC circuit. And this unit of flux, which I really don't care. I'm not too much, you could tell I'm not too much on the theory of these. And I don't really care too much about the theory of these. And you get a physics class and you can do that. Right now, we're interested more than anything else in looking at the equation for when something happens, what it is, and I'm not too interested in this part of it. So again, you can read through this, but it's not where we're going to camp on. Here is some inductor that is for various things. We have inductors in our class, and I give them to you. They look like that right there. They look exactly like that. Okay, and there's the symbol for an inductor. Different symbols: tunable inductor, straight-hole inductor, and with a core. Anyway, now how do you combine them? Right? If you're out in the forest, you're alone, you're the last person alive, and you're trying to build something up electronically, and you find just a big storehouse of inductors, and you have to use inductors to do it, but you don't have the right ones, what do? They are just like resistors. They're not the opposite of resistors, they're just like resistors. So here would be, this would be in series with the parallel combination of these two. So you'd find the parallel combination of these two, add it to that, you've got your answer. So inductors are just like resistors, capacitors are the opposite. That's how that's done. Not a big deal, but again, that's how it's done. Okay. And with respect to voltage and current, this is your relationship. Instead of V, sometimes we use the term E, and this means Eli. E equals L di over dt. Ice, Eli the Iceman, I equals C dV over dt, which basically says if you have an instantaneous change of current, what do you have? If the current could do this, what would you have for voltage? What would voltage do? What's the derivative of a step function? Right here it's 0, right here it's 1. If you shrink time down, the I over dt and t is 0. The derivative is, if anything over 0 is what? A very big number, infinity and beyond, right? So you may think, what is he talking about? Well, okay, so somebody has a little thing that they bought from a game shop or whatever, and it's a pack of cigarettes, and you pick it up and you get a shock. How do they do that? Do you get a shock from that little battery inside directly? I mean, if you pick up that little battery that's inside, how do they do that? How do you get a big voltage out of a little voltage like that? Put a switch in that little battery, and you get a change of current through an inductor that is very high. In other words, you try to simulate this. So V is equal to that. So you're actually looking at this thing and you're picking it up, and a little switch on the bottom activates, which basically gives you a very high value. It tries to make that current go like that. Okay? And that gives you a shock. You say, so I got a shock because of the inductor? Yes. You got a shock because you drove the dt to 0 or close to 0. And you say, will it kill me? No, it's not going to kill you. It's just and then you go on with your life. How many of you ever had that happen? Picked up something that somebody's a game thing and you picked it up and it shocked you. There it is. And that's why it happens. All right? It's through an inductor, a switch and an inductor, and a little battery, boom. Little simple circuit. You say, that's all it is? That's all it is. But it's because of that equation, and you drive the dt, or the change in time, to almost 0. It isn't exactly 0, but it's you have a real pulse of voltage. Boop, and then done. We're done. Any questions anybody's got? See you next Tuesday. Take care.